Hi everyone. So today we're going to discuss solubility of ionic compounds. You might have noticed in our previous lecture that sometimes when we mix two liquids together, we actually end up with a solid or a precipitate. So how do we know when something is going to precipitate or turn into a solid? So many reactions take place between compounds or elements that are dissolved in water. Ionic compounds and some polar covalent compounds break apart or dissociate when they dissolve in water and form ions. But other compounds can form solids. Now, if something can dissolve in water, it's referred to as soluble. But if something generally doesn't dissolve, then we say that it's insoluble. So down below we have a chart for general solubilities of ionic compounds in water. So let's start with the first set here, group 1A metals in their ionic form, and the ammonium ion. So group 1A metals, again, are sodium, potassium, etc. And so those are always soluble in their ionic form. And there are no exceptions. So no matter what those metals are bonded to, or whatever compound they're in, they'll always want to dissolve or break apart from the ion that they're bonded to. And then the next set here are nitrates. Nitrates are also always soluble. So anything bonded to a nitrate, that compound will dissolve in water or break apart in water. And then acetates are also always soluble. Chlorides, so if something's bonded to a chlorine ion or a chloride ion, that is also typically soluble, but there are some exceptions. So if a chloride ion is bonded to silver, lead, or mercury, then it will be insoluble. So those are the very specific exceptions. And then sulfates are typically soluble unless the sulfate ion is bonded to barium, strontium, lead, or mercury. And then it will be insoluble, so it will form a solid in solution. And then carbonates are generally insoluble. So if something is bonded to CO3, the polyatomic ion carbonate, then it's typically going to form a solid in solution unless that carbonate is bonded to something that is always going to dissolve, like the ammonium ion or group 1A metals. So those are the exceptions. If carbonates are bonded to a group 1A metal or the ammonium ion, then it will dissolve in solution because those two categories are always soluble. And then phosphates are generally insoluble as well, unless, again, they're bonded to something that is always soluble, like a group 1A metal or the ammonium ion. So I'm going to make some flashcards for you that you can use to remember these rules. These are really important rules to remember. Okay. So let's go over a few examples of different compounds and determine if they are soluble or insoluble. All right. So let's start with NaNO3. So this is sodium bonded to nitrate. And let's divide this up into its separate ions. So we have a sodium ion and a nitrate ion. And if we go back to our rules on the last slide, remember sodium is a group 1A metal ion, and that is always soluble. And then just below that are the nitrates, which are also always soluble. So that tells us both are always soluble. So that means that sodium nitrate is soluble. So again, that means that it will dissolve in solution. And if something can dissolve in solution, we would write a little aqueous symbol next to it. So that means that it's dissolved in water. All right. Now let's look at the next one, sodium carbonate. So we have 2 sodium ions. So remember, this little subscript tells us how many of each component we have. And then that's bonded to the carbonate polyatomic ion, which has a 2- charge. All right, so we already said that sodium ions are always soluble, but let's go back and check the carbonate ions. Oh, if my PowerPoint will let me. Apparently not. Let's see if I can go the next slide. There we go. All right, so the carbonates are the second to last category, and it says that they are generally insoluble unless they're bonded to group 1A metal ions or the ammonium ion. So in our case, carbonate is bonded to a group 1A metal, so this compound would be soluble. So here I'll put a little note under each. So sodium ions are soluble, and carbonate ions are insoluble unless bonded to group 1A metals or the ammonium ion. All right, so next, or actually let's add a little aqueous designation there. All right, next is silver bonded to chlorine, or the chloride ion. So let's divide this up. So chlorine always has a -1 charge. So that must mean silver has a +1 charge. All right, and let's look at the category of chlorides on the previous slide. So chlorides are in the middle of our table, and it says that they are soluble unless they're bonded to silver, lead, or mercury. Okay, so in this case, it is bonded to silver, so that's one of the exceptions. So that means that this compound is insoluble, so it does not dissolve in water. So in that case, we're going to put a little S in parentheses next to silver chloride because it will become a solid or stay a solid in solution. All right, and then the next compound is ammonium phosphate. So we have 3 ammonium ions and 1 phosphate ion. And let's go back to our chart and look up the phosphate group. Oh, there we go. So phosphates are the last group in our table. And it says that they are insoluble unless bonded to a group 1A metal or the ammonium ion. All right, so in this case, phosphate is bonded to ammonium ions, so this would make it soluble. because ammonium ions are always soluble. So then we'd write a little aqueous designation there. And then in our last example, we have barium sulfate. So sulfate, remember, has a 2- charge, and barium has a 2+ charge because it's in the group 2 metal ions. All right, so let's go back to our chart. Oh, my PowerPoint is really struggling today. There we go. Let's see if it lets me go backwards. Okay, so sulfates are, let's see, kind of in the middle of our table there. And they are soluble unless bonded to barium, strontium, lead, or mercury. So that means for this compound, because sulfate is bonded to barium, it will be insoluble. So it would be a solid. Okay. And then here is the solution slide if you need that later. Now, when you form a solid in a reaction, we can call that reaction a precipitation reaction. So we're producing a precipitate. Now, these are also double replacement reactions, which we talked about in the last lecture. So for the reaction below, let's determine if the products are insoluble or soluble. So in the reactants, we have sodium chloride, which is dissolved in water, so it's aqueous, and that's reacting with silver nitrate, which is also aqueous. So remember, sodium ions are always soluble, and then nitrate ions are also always soluble. So both of these compounds will be soluble. Now, this is a double replacement reaction. So in this reaction, sodium and silver are going to trade places. So we're going to end up with silver chloride as one of our products and sodium nitrate as the other product. Now let's see if one of these products is a solid. So on the last slide, we saw that for AgCl, chlorides are generally soluble unless paired with certain ions. And one of those ions was silver. So because the chloride ion is bonded to a silver ion, this would be a solid. And then for the other product, we have sodium and nitrate, which are always soluble. So this would be aqueous. Now, if we look at a beaker with each of these products or ions in solution, we have a solid, which will probably sink to the bottom. So that's our AgCl. And then we have our aqueous product, sodium nitrate. So when we say that something's aqueous, remember that means it's dissolved in water or it has broken apart. So we would actually have separate sodium ions and nitrate ions floating around in solution. So they're not actually forming a molecule necessarily, they're just floating around. But that's why we write aqueous next to it to indicate that the ions are dissolved or dissociated in water. Now, part of the reason that these molecules can dissolve is due to the polarity of water. So remember, water looks like this, where we have an oxygen bonded to 2 hydrogens. And then remember that we have a partial negative charge on oxygen and a partial positive charge by the 2 hydrogens. Now, if we have a salt, like let's say NaNO3, so let's say initially sodium nitrate is a solid, and then we add it to water. We would have alternating sodium and nitrate ions, because remember, ionic compounds form a crystal lattice. And water can actually start to form some ion dipole interactions. So let me draw water in blue here. So if we add this solid to water, water's going to orient itself in such a way that the partial positive part of the molecule is attracted to the negative charges, and then the partial negative part of water is going to face the positive charges. Eventually, water can start to pull those ions away and separate them from each other. So in solution, for instance, we would see water molecules surrounding each ion and kind of forming a little circle around each of them. So it might look something like that if we could actually zoom in on our beaker. Now, silver chloride, we said, is a solid in solution. And what that means is water is not strong enough to pull apart silver and chloride ions. Silver and chloride ions are so attracted to each other that they really cannot be pulled apart by any other force present in our beaker. Okay, so now that we've figured out how to determine which products are aqueous and which ones are solids or precipitates, let's focus a little bit on how to write ionic equations. So the equations for reactions that occur between dissolved materials can be written in three ways, called molecular equations, total ionic equations, and net ionic equations. So down below, we have the same reaction that we just wrote out, where sodium chloride is reacting with silver nitrate to produce silver chloride and sodium nitrate. So that would be our molecular equation. So everything looks like a molecule. However, we know that if you have an aqueous reactant or an aqueous product, the ions are actually separate from each other and they're floating around solution. So then we could write the total ionic equation, which is shown in blue down here, where we draw out or write out the different ions that are present. However, we would leave the solid as one molecule because remember, that's not forming ions in solution. It's just a solid that kind of sinks to the bottom. And then finally, we can write our net ionic equation, which shows the actual reaction that's occurring. So if we look at our ions, we can see that sodium doesn't do anything in this reaction. Sodium just stays an ion that's dissolved. Similarly, nitrate just stays as an ion floating around solution, so it's not really doing anything or reacting with anything. So those are what we call spectator ions. They're just watching everyone else react. They're just kind of hanging out in the background. So our net ionic equation will be whatever's left over after we kind of cancel out the spectator ions. So chlorine, or the chloride ion, and the silver ion are what's actually reacting in solution to form a solid. So this would be our net ionic equation. So again, these are just three different ways that we can write out ionic equations. So again, in a molecular equation, each compound is represented by its formula. So for instance, even though we know that sodium nitrate is going to be broken up into its separate ions in solution. In a molecular equation, we just write it as sodium nitrate, as if it is a molecule. And again, in total ionic equations, all soluble ionic substances are represented by the ions they form in solution. Substances that do not dissolve, or that dissolve but do not dissociate into ions, are represented by their formulas. And down below we have a figure again of water surrounding different ions and kind of pulling them apart from their original crystal lattice. And again, we would want to represent that an ionic compound is soluble by writing out the individual ions for that compound. And that would be within the total ionic equation. And again, net ionic equations, only unionized or insoluble materials and ions that undergo changes as the reaction proceeds are represented. So remember, our silver chloride product was the only thing that formed a solid. So we just showed the ions for that compound and then the final product. So any ions that appeared on both the left and right side of the total ionic equation are called spectator ions and are not included in the net ionic equation. Okay, so let's go over an example. Let's write the following molecular equation in its total ionic and net ionic forms. Soluble substances are indicated by aqueous after their formulas, and insoluble solids are indicated by S, or solid, after their formulas. All right, so for this reaction, we have barium chloride, which is aqueous, and sodium sulfide, which is aqueous. And then in the products, we have barium sulfide, which is a solid, so that's our precipitate. And then sodium chloride, which is aqueous. Now, you'll also notice that there's a 2 in front of sodium chloride. That's to balance out the number of atoms. All right, so in total ionic form, all substances except the insoluble barium sulfide will be written in the form of the ions they form. So let's write this out. So in our reactants, we have barium and chloride. So remember, barium is a group 2 metal, so it will have a 2+ charge. And then there's actually 2 chlorides there, so we're just going to write 2Cl-. And then in the next reactant, we have sodium sulfide, and there are 2 sodium ions. So we'll write 2Na+. And then we have sulfide, which has a 2- charge. Remember, it's in group 6A, so it needs 2 more electrons to have an octet, which means it ends up with a -2 charge. All right, and then in the products, we have barium sulfide, which we'll just leave as barium sulfide because it's a solid. And then we have 2 sodium ions and 2 chloride ions. All right, so let's try to find our spectator ions. Which ions are not reacting with anything? All right, so hopefully you said sodium. Sodium is not really doing anything in this reaction. It's just kind of hanging out. And then also chlorine. The chloride ions aren't really doing anything. They're just hanging out. So what's left over is our net ionic equation. So in net ionic form, all spectator ions are dropped. Both the sodium and chloride ions are spectator ions because they appear on both sides of the equation. So I guess the answer was kind of given to you there. So we'll end up with barium, which is aqueous, and sulfide, which is also aqueous, and those are going to react to produce barium sulfide, which is our precipitate. Okay. So again, we have our molecular equation at the top, our total ionic equation in the middle, and then our net ionic equation at the bottom. Now let's identify the products for this equation and balance the equation. So let's figure out how to actually determine the products for a precipitation reaction. All right, so in this equation we have, or this reaction, we have silver nitrate and magnesium chloride. And remember that the metal ions in this type of reaction are going to switch places. Now, when I solve for these types of reactions, I like to kind of write out the ions individually just so I can kind of see what the charges are and how they'll balance when they switch places. So in silver nitrate, we have Ag+, so silver always has a +1 charge, and then nitrate always has a -1 charge. And then magnesium has a 2+ charge always, and chloride ions have a -1 charge always. Okay. So now we're going to switch around silver and magnesium. So in our products, silver and chloride are going to team up, and silver has a +1 charge, and chloride has a -1 charge, so they perfectly balance each other out. All right. Now our other product, magnesium, is going to pair up with nitrate. However, I'm going to draw down here. Remember, magnesium has a 2+ charge. Nitrate has a -1 charge. So how many magnesiums and how many nitrates do we need to balance the charges? So hopefully you said that we need 2 nitrates in order to balance those charges. So what we'll do is we'll write this as Mg, and then remember for polyatomic ions we have to put parentheses around it if there are multiple polyatomic ions. So we'll write NO3, close our parentheses there, and then we'll put a subscript 2 after that. So when you're figuring out these types of reactions and what their products are, because we're usually dealing with ions here, we do have to balance the ionic charges first, and then we can balance the atoms on both sides of the equation. So now let's balance the reaction. All right, so we do have, let's see, let's write out a table so we can balance this properly. So we have 1 silver in the reactants and 1 in the products. And I'm actually going to treat nitrate as 1 unit here because that will make it much easier for balancing. All right, so we have 1 nitrate ion in the reactants, and we actually have 2 nitrate ions in the products because remember we needed 2 nitrates to balance our 1 magnesium. Okay, so our next item is magnesium. We have 1 in the reactants and 1 in the products. And then the last one is chlorine, or the chloride ion. So in the reactants, we do have 2 chloride ions, and in the products, we only have 1. Okay, so let's start balancing. Let's start with nitrates. So we do need 2 nitrates in the reactants, so I'm going to put a 2 in front of silver nitrate. Now, that also changes the number of silver ions to 2. So now let's go back and balance the silver ions. So if we have 2 silver ions in the reactants, we also need 2 in the products. So let's put a 2 in front of AgCl. All right, so now we have 2 silver ions, but that also changes the number of chloride ions. All right, so now is there anything left that we need to balance? Nope, looks like everything is balanced. We have 2 silver ions on each side, we have 2 nitrate ions on each side, we have 1 magnesium on each side, and we have 2 chlorines on each side. Perfect. Now let's figure out which product is our solid. So remember from before, silver chloride has a really strong bond, and it's going to be insoluble. So that will be our solid. And then magnesium nitrate is aqueous because nitrate is always soluble. Okay, so let's kind of write out a general flow chart here for this type of problem. So 1, balance ionic charges. And when you balance ionic charges, you're going to use subscripts. And then 2, balance atoms on each side of the arrow. And when we do that, we use coefficients. So remember, we're not going to change the subscripts during this step, only the coefficients. And then 3, determine if there is a precipitate. And so for that, we would use our solubility rules. All right, so now the next step would be to write the ionic equation and the net ionic equation. All right, so let's start by figuring out what was aqueous. So silver nitrate and magnesium chloride were both aqueous reactants. So we're going to write out all of those ions separately. Okay, so we had silver, which was a +1 ion. Oh wait, silver was bonded to nitrate. I'm getting ahead of myself. All right, so we had NO3 minus, and then we had magnesium 2 plus, and we actually had 2 chloride ions bonded to magnesium, so I'm going to write 2Cl minus. And then in the products, we had silver chloride, which was a solid, so we'll leave that as it is. And then we had a magnesium ion and 2 nitrate ions. Okay, so now we need to identify our spectator ions. So which ions are not reacting with anything in this reaction? So hopefully you said magnesium and nitrate. So we can actually cancel those on both sides in order to write our net ionic equation. Oh, and I actually forgot, we have 2 silver ions and 2 nitrate ions from our previous balancing. And we have 2 AgCl as well. That's my fault. I totally forgot that we balanced our equation. Okay, so now let's write out our net ionic equation. So we have 2 silver ions, which are aqueous, and then 2 chloride ions, which are aqueous, and we're producing 2AgCl. Now, in this case, we could probably just get rid of all the 2's because we have a 1:1:1 ratio between the reactants and the product. Or you can leave it like this. That's totally fine too. But we could have also written this as Ag plus Cl minus produces AgCl. That is also totally valid. Okay. So hopefully this helps a little bit with understanding ionic equations as well as double replacement reactions and precipitation reactions. So remember to balance ionic charges first when you're trying to determine what your products are. And we balance those using subscripts. And then second, remember to balance the atoms on both sides of the arrow. And in that step, we'll use coefficients. And then 3, determine if there is a precipitate. Okay. So one more thing I wanted to cover is energy. So in addition to all of the changes that take place during a reaction, chemical reactions are also accompanied by changes in energy. So reactions will either absorb energy or give up energy as they proceed. The energy that's involved in these chemical reactions can take many different forms. So, for instance, some chemical reactions will release electrical energy, such as in our cell phone batteries. However, in a lot of reactions, energy takes the form of heat. And I do have a YouTube video showing that type of reaction. We have to watch that.
Hi, sir. You wanted to see me?
Yes, that night. Please take a seat.
All right, we'll skip the ad there.
Here I'm working with some lithium metal, very difficult to cut. I've got a piece of sodium here, pretty easy to cut. You notice when I cut through that the fresh sodium is very shiny compared to the rest. Let's zoom in real quick. Let's see if we can really get in there. So this side will reflect a lot of light. The other sides are pretty dull. And you'll see that especially with the potassium here. I'm going to go ahead and give this kind of a half cut. So for the potassium, this is the side that's freshly cut, and you can see the dullness to the other sides compared to that one. So I'm going to go ahead and take those 3 and I'm going to add them to water, and we can look at the kind of reactivity of those 3 alkali metals with water. So here I'm going to take the lithium and add that to the water. It's going to generate hydrogen gas and lithium hydroxide. So you're going to see a pink color develop here, and then you're going to see some smoke come off, and that's either lithium metal or that's lithium hydroxide coming off of there. Maybe a little bit of liquid water. But it's not as reactive as, say, sodium, so I'm going to put sodium into the next one. And the sodium is actually probably going to ignite. So you'll see some orange flame perhaps, or some sparks, or some shrapnel. And then the last one, I'm going to go ahead and put my 2 pieces of potassium in that I've cut in half. So this is less potassium than the other 2 in terms of amount. But you'll find that the reactivity is a little bit greater.
Okay, so you could probably tell that those were pretty, in some cases, explosive reactions, and they were giving off heat. And so we would call that an exothermic reaction. So chemical reactions that release heat as a product are called exothermic reactions. So another example of that is if you have a fireplace at home and you put logs in and light them up. Combustion of a log in a fireplace is an example of an exothermic reaction. So you're producing heat. Now, while this is a physical process, not chemical, if you melt ice, that's an example of an endothermic process because the ice is absorbing heat, so endothermic, and it's melting. So exothermic again means that something is releasing heat, and endothermic means that something is absorbing heat. Oh, I don't know how I zoomed in. Okay. So one way that I remember this, exo means outside of, endo means inside of. So exo, you're kind of exiting, so the heat is exiting the system. Endo, something is entering the system. So that's one way to remember it. Now, an example of an endothermic reaction is in the video below.
What I have is some barium hydroxide. Okay, I'm going to put this into the... In fact, you know what? I'm going to do this in one of the beakers, not that thing, because it's ridiculous. Barium hydroxide, and I've got some ammonium chloride. Now, what I'm going to do is mix these together, and hopefully we should see a endothermic reaction. Yes.
It's with the hand stuff.
What hand stuff?
The hand sanitizer gel.
Oh, it just lives on my desk. Oh. I was chopping up hearts earlier, and yeah, I need to be not covered in blood. So, what I'm going to do to show how exothermic this is, how much heat this is taking in, I'm going to make this wooden block wet. Okay? Now, you will see why I've done that in a second. So, I'm going to mix these two things together, and carefully, I need to break that up a bit. Mix these two things together. Well, hopefully not, because if it's blowing up and giving out huge amounts of energy like that, that would be what type of reaction? Exothermic. Now, we want to see endothermic, so it's going to be a little bit more subtle. So, I mix the barium hydroxide and the ammonium chloride together, and they should start to react.
Does it freeze it?
Well, we should soon see. So they're mixing together. Now, can you see how the consistency of that is changing slightly? It's sort of clumping together, because one of the products it's making is water in this reaction. And you can see actually that's all gone liquid, and it was all just solid powders. It's not milk. You wouldn't want to put it in coffee.
Oh.
Okay, if you put that in coffee, there'll be problems. Now, one of the products of this, because it's ammonium chloride, is it's giving off ammonia, which smells rather horrible. And I'd forgotten about that, which is why I just breathed the huge load in. That sort of horrible, slightly tangy smell in wee is sort of ammonia-like.
Oh, is that what I can smell?
Yeah, that's what you can smell. Unless you've wet yourself, that is the best one you can smell. Okay, but also, actually, this is getting actually very cold as it's going along. Okay, now hopefully, if this has worked, it's getting cold enough. Well, I put water on the base there.
Yeah.
Fingers crossed. It's actually frozen the water onto the bottom. Now, this reaction has worked so well, so much energy has had to be taken out of the environment. It's got that water so cold that it's dropped below freezing and frozen onto the bottom. That is pretty cool.
How cold is it?
Okay, so in that reaction, barium hydroxide and ammonium chloride were mixed together, and they absorbed heat as they reacted. So because the reaction was absorbing heat from the surroundings, it caused the water underneath it to freeze. And so eventually the beaker was frozen to that wooden block. This is also similar to ice packs. Ice packs contain ammonium nitrate, and when you kind of break up an ice pack, the ammonium nitrate reacts with water and absorbs heat from the surroundings. So when you place an ice pack on your skin, it's absorbing heat from your skin, and so it feels cold. So this is, one more really cool part of chemistry is we can manipulate certain properties of chemicals to, release heat and make something warm, or absorb heat and make something cold. So that's all I have for this lecture. In the next one, we'll continue chapter 5, and I will see you then.